In the last classes, we've been talking about least squares fitting. We developed our own code for least squares fitting of straight lines. We used a library code, curve fit, for least squares fitting of straight lines and polynomials and other functions. When we were doing the least squares fitting, we talked about the importance of the chi-squared, the residuals, the parameter uncertainties, the parameter correlations, and we looked at some examples from astrophysics and also from subatomic physics. Today's class, I want to move on to a new topic, a new module. I want to talk about numerical solutions of partial differential equations. And when we talk about numerical solutions of partial differential equations, we'll either be considering what we call boundary value problems, where the potential or the solution is specified on the boundary of the problem, or we'll be talking about initial condition problems, where the potential or the function is specified by the initial conditions. Over the next few classes, we'll look at illustrations from electrostatics, thermodynamics, and wave dynamics. Today's class, we're going to focus on electrostatics, and electrostatics is a big area, a big topic for partial differential equations. So, coming to electrostatics, I wanted to remind you first of two basic classes of problems in electrostatics. So one class of problem in electrostatics, I'm going to call it the easy class, is where you want to figure out the electrical potential or electrical field, and you know the charge distribution. In that class of problem, where you want the electrical potential, electrical field, and you know the charge distribution, the solution to the problem is simply one of either addition or one of integration. That is, you need to sum up the electrical potentials of all the individual charges or of all the individual charge elements. You have to sum them up or integrate them up to get the total electrical potential. The second type of problem is where you want to calculate the electrical potential, electrical field, knowing some boundary conditions on the electrical potential, electrical field. So in this type of problem, we solve what's called Laplace's equation or Poisson's equation. It depends on whether you've got charges or you haven't got charges in your region of interest, in your space of interest. You solve Laplace's or Poisson's equation by matching the solution to Laplace's or Poisson's equation to the boundary conditions, to the potentials or the fields at the location of the boundary conditions. So in today's class, we're going to explore the solution of Laplace's and Poisson's equation. I wanted to begin by just reminding you where Laplace's or Poisson's equation come from. That is how you derive Laplace's or Poisson's equations. Then we're going to remind ourselves of the ways in which we might have solved Laplace's Poisson's equation in, say, a course, undergraduate course, graduate course on electrostatics. One way we would have solved it is method of images. Another way we might have solved it is separation of variables. So we'll remind ourselves of those ways. And then after that, we'll move on to discussing the numerical solution of Laplace's equation. Now, there's an important point here. The method of images for solving Laplace's or Poisson's equation applies to a very restricted small set of problems. The separation of variables as a way of solving Laplace's Poisson's equation also applies to a pretty restricted set of problems. On the other hand, the numerical solution of Laplace's or Poisson's equation, that's very, very powerful. With the numerical solution of Laplace's Poisson's equation, you can essentially compute any problem. Anyway, let's chat about where Laplace's and Poisson's equations originate from. They originate from the field properties, field characteristics of the electrostatic field, and the field characteristics properties of the electrostatic field are determined by its flux and its circulation, or using differential vector calculus, its divergence and its curl. So you probably remember that the electrostatic field has a divergence. That's where field lines begin or field lines end. And the equation for the divergence is this little guy here. The divergence at any point in space is equal to the charge density at that point in space, divided by epsilon naught. Regarding the curl or circulation properties of the electrical field is curl-less. It has no circulation. So we could write that down as the curl of the electrical field is 0. A consequence of that, which is what I've written down here, is that you can express the electrical field in terms of an electrical potential, phi, where the electrical field is the negative gradient of the potential. So this expression here is equivalent to a curl-less, a circulation-less field. It's out of these two field properties, it's out of these two field equations that you can build Laplace's Poisson's equation. Actually, all you have to do is plug the equation on the right for the electrical field in terms of the electrical potential into the equation on the left that specifies the divergence of the electrical field. And you get, as I've indicated downstairs here, Laplace's equation, which simply says that the Laplacian of the electrostatic potential is equal to, if you've got charges in some region of space, negative times the charge density divided by epsilon naught. And if you haven't got charges in that region of space, it's actually just equal to 0. And that's Laplace's or Poisson's equation. You can see that they're second order differential equations involving the electrostatic potential, defining the electrostatic potential. Poisson's equation, excuse me, Poisson's equation is one that we call an inhomogeneous differential equation. Laplace's equation is one that we call a homogeneous differential equation. Laplace's equation describes a region of space in which there are no charges, no exposed charges. Poisson's equation is one which describes a region of space in which there are charges present. So before I discuss the ways that we might solve Laplace's or Poisson's equation, again, method of images, separation of variables, and more generally numerically, I just want to remind us of what we call the uniqueness theorem. And that theorem applies to Laplace's and Poisson's equation. It says basically that if just somehow, by some magic, by some guess, you come up with the solution to Laplace's Poisson's equation, or you come up with a solution to Laplace's Poisson's equation that fulfills the boundary values, the boundary conditions of your problem, then that solution that you've somehow came up with is necessarily the unique solution to your particular problem. It just says that no matter how you find the solution, if it solves your problem, it is the unique, correct solution. So that somehow coming up with that unique solution might be guessing the unique solution. That's sort of what the method of images is. It might be deriving the unique solution. That's kind of what the separation of variables is, or it might be numerically computing the solution. And that's what we're going to focus on in today's class. So that's the uniqueness theorem. And that's a very important theorem that applies to Laplace's, Poisson's equations, but also partial differential equations in general. So now I've got a slide on the method of images for solving Poisson's or Laplace's equation. I've got a couple of slides on the separation of variables for solving Laplace's or Poisson's equation. The purpose of these slides is to remind you of methods you already know for solving Laplace's or Poisson's equation. But the other purpose of those slides is to realize or recognize the limitations of these methods for solving Laplace's or Poisson's equation and the value of the numerical approach that we're going to discuss for solving Laplace's Poisson's equation. So let me start with the method of images. As I say, the method of images is sort of, kind of like guessing the solution to your problem and checking that it matches the boundary conditions of your problem. So here's the most famous example of the method of images. In this particular problem, we're asked to imagine a region of space that has a single positive point charge, here it is in green, and a planar grounded conducting sheet. Here it is, this vertical line. And we're asked to figure out the electrical potential in the region over here to the right of the grounded conducting sheet. So that's the question. So at first sight, this might look like a rather complicated problem to solve. It's a rather complicated problem to solve, in part because you don't know how the charge is distributed on the sheet. You only know that the electrical potential is 0 on the sheet. It's also complicated, you can see, because the pattern of field lines in the neighborhood of the charge, in the neighborhood of the sheet, is quite complicated. So in the method of images, instead of solving a problem of a conductor and a charge, or in general, conductors and charges, we solve a problem that involves just charges. That is easy to solve because you've just got to add the potentials of the charges. And we show that that solution to that problem of just charges actually matches the boundary conditions for the problem involving the conductor and the charges. So the solution to this particular problem of a conductor and a charge is obtained from this familiar situation of an electrical dipole. A positive charge over here on the right, negative charge over here on the left, some separation between the two charges. Between the two charges, on this bisector of the two charges, the electrostatic potential of the positive charge on the right is cancelled by the negative charge on the left. So this is an equipotential of 0 electrical potential. And that, you realize, exactly matches the boundary conditions of our planar grounded conducting sheet and the positive charge on the right-hand side of that sheet. And so this arrangement of a positive and negative charge creates a electrical potential and also an electrical field that exactly matches our problem. And so this solution that I've written down here to the problem of the single positive point charge in the grounded conducting sheet is just the electrostatic potential of one positive charge located at x equals a distance a from the grounded sheet towards the right, and a second negative charge at a distance minus a from the grounded sheet towards the left here. It's just the sum of the potentials of those two electrostatic potentials of those two charges. And this solves the problem of the electrical potential everywhere in this region of space to the right of the conductor that corresponds to our problem. And we've solved it by the method of images. So that's really a kind of neat technique. It's a rather limited technique. There's only special cases. There's only a catalog of small cases where you can do this trick of replacing a combination of conductors and charges with just charges and identify that the problem involving just charges looks exactly like the problem involving the charges in the conductors, i.e. the fields and the potentials. A somewhat more general approach, but actually not much more general approach for solving Laplace's or Poisson's equation is the approach that we call separation of variables. So in this approach, we have a problem where we want to solve Laplace's or Poisson's equation, knowing the boundary values for the electrostatic potential at some locations. And we take Laplace's equation, Poisson's equation, we write it down in some explicit coordinate system, say rectangular coordinates, and we hypothesize, we suggest a solution in which the electrostatic potential is a separate function of the spatial coordinates. So in rectangular coordinates, be separate functions, say, of x and y and z. And then that's separating the variables. We turn our partial differential equation, that's Laplace's equation or Poisson's equation, we turn it into ordinary differential equations. And then we solve those ordinary differential equations. That gives us a family of solutions. And then we match that family of solutions to the boundary conditions of the problem. So to just remind you of that method, let's just go quickly, and I'm really going to go quickly, so I'm not going to explain all the details here. Let's go quickly through this particular problem I've sketched over here on the left-hand side. So in this particular problem, I've got a horizontal conductor at constant positive electrical potential, call it phi naught. I've got two tall, infinitely tall, vertical conductors, one located at x equals 0, one located at x equals L. They're grounded conductors. And finally, at large values of y, far from the positive conducting sheet, we've also got 0 potential. So that's the arrangement of the conductors, and that's a description of a boundary value problem. We know the electrical potentials downstairs here on the lower edge of the problem, left and right, we know the potentials, and way upstairs, infinitely far away from the horizontal conducting sheet, we know the potential. And we want to find the potential as the field everywhere inside that volume. So we're going to write down Laplace's equation for that situation. We're going to write it down. Firstly, we're going to write it down in rectangular coordinates. because that's a natural coordinate system for this rectangular problem. We're going to write it down in 2 dimensions, just x and y. So by writing it down as a 2-dimensional problem, we're assuming that in the 3rd dimension, so that's into the screen and out of the screen, the electrostatic potential is just constant. That's kind of assuming that these horizontal vertical plates extend infinitely far into and out of the screen. And so we're going to go ahead and solve this version of Laplace's equation, this 2nd-order partial differential equation with respect to x and y. As I say, in this method of solving by separation of variables, we're going to hypothesize that electrostatic potential can be written as a separate function of x and y. So I've written that hypothesis down here. I've said that the electrostatic potential, which is in general a function of both x and y, can be written as this product of the function uppercase x, that's just a function of x, uppercase y is just the function of y. Now look, I don't know that that's true. That might not be true. If it turns out to be true, this is a way of solving the problem. If it turned out not to be true, it would not be a way of solving the problem. As an example, if the potential was just x times y times z, that would be a potential that's separable. I could write it as a product of 3 separate functions of x, y, and z. If the potential was x plus y plus z, that isn't separable. I couldn't write that potential as a product of 3 separate functions of x only, y only, z only. Okay, so this looks like a scary, horrific slide. It is sort of a scary and a horrific slide. It contains all the details of the solution of this problem, from starting with Laplace equations, the partial differential equation, to the final solution expression for the electrostatic potential in the region inside the box. As I say, I don't want to go through every little detail of this or that in this problem. I just want to remind you of the basic steps in solving this problem. I want to remind you that it's quite a bit of work to solve this problem, which is a relatively simple separation of variable boundary value problem. It's even a lot of work for this problem. And that will introduce us to the advantage of the numerical method for solving these types of problems. Anyway, let's walk quickly. Let's not worry about every detail. Let's just get a feeling for what we do. So here's Laplace's equations, partial differential equation, 2nd-order partial differential equation of the electrostatic potential with differentials with respect to x and y. Here's my hypothesis that I can write the potential phi as a product of separate functions of x and y, uppercase x and y. If I plug them in, if I replace phi with x times y inside the differentials, of course, if I'm differentiating with respect to x, I can pull the y out front. If I'm differentiating with respect to y, I can pull the x out front. Now, here's a useful thing to do. Supposing I divide this expression here by the product of x and y. For the first term, if I divide by x times y, I'm going to cancel out the y. And this first term only depends on the function x and its differential. For the second term, if I divide by the product of x times y, then this second term is going to be 1 over y times the 2nd-order partial differential of y. It only depends on y. So by dividing by x times y, these 2 terms, I make the first term just a function of x, the second term just a function of y. That means an important thing. It means that no matter where you are in x for this first term, it must be equal to some constant value. No matter where you are in y for this second term, it must be equal to an equal and opposite constant value. That's the only way to ensure that the sum of the two terms is zero. So that's a very important point. After dividing by x times y, the first term is a constant, the second term is a constant. They're equal and opposite constants. And so that's what I wrote down here. On this second line, I turned the single partial differential equation into two ordinary differential equations by recognizing that the two terms are equal and opposite constants. I called the constant beta squared. I set the function of y, x, equal to beta squared. Then that term that involves the function of y is equal to minus beta squared. And then I just rearranged those two now ordinary differential equations to see that the first one simply says that the second order differential of x is proportional to x, and beta squared is the coefficient of proportionality. And the second equation now says that the second order differential of y is proportional to minus y, with beta squared being the coefficient of proportionality. Now, these two equations here, they have well-known solutions. So the solutions of equations where the second order differential of a function is in proportion to the function or in negative proportion to the function are well known to us. They're the exponential functions and they are the sinusoidal functions. So the exponential functions, we can think of functions with a real exponent. The sinusoidal functions, I'm going to think of those as exponential functions with an imaginary exponent. And so here I just wrote down the general solution now of this partial differential equation. And I got it by realizing once I split it into two ordinary differential equations, and once I spotted the solutions of those ordinary differential equations, I just filled them in to construct the general solution of Laplace's equation. Now, a few comments on this line here. A1, A2, B1, B2, they're just coefficients. So this is a massive, massive family, infinite family of general solutions with different values of A1, A2, B1, B2. Beta, this is this constant that emerged from separation of variables. You see that it's in the exponents here. It's a smooth, continuous variable at this stage. It too could take any values. Now, I've written, if you look here, I've written the x dependence as involving the imaginary exponential arguments and the y dependence as involving the real exponential arguments. And the reason for that is a certain feature of this particular problem, that as you go to large y, as you go way up the walls of that U channel that we're trying to solve the problem of, as you go to large y, the potential's got to go to zero. So you'll see that in the next lines. I'm going to use this form for the general solution in the next lines of this slide. There is actually 4 lines here, and they correspond to applying the 4 boundary conditions in this problem. So there's a boundary condition for y being infinitely large, where the potential goes to 0. That's this guy here. And there's a boundary condition for when when x is 0. That's the left-hand plate. That's this boundary condition here. There's a boundary value for when x equals L. That's the right-hand plate. That's this boundary condition here. And then there's finally a boundary condition for the bottom plate. And this should actually be the value of x that is variable and y being 0. So there's a mistake here on this slide. Okay, so let's just walk through the application of these different boundary conditions. So in the first step, I say, I'm going to ignore this term involving B1 here, because I need to ensure the electrostatic potential is 0 at large y. And so I'm just going to keep this second term here. When I keep this second term here, I'm just going to absorb the B2 into the A2 and the A1. So that's how I jump down to here. Next boundary condition. I've got to ensure that on the left-hand plate, the potential is 0 everywhere. The only way to assure that is that, so that's for any value of y, this has to be 0. I'm going to have to make this coefficient here, A1, and this coefficient here, A2, equal and opposite. And so I apply that boundary condition. And now I've just got, instead of A1 and A2, I just got one coefficient. I called it A. I also, in this step, rewrote this combination of positive and negative imaginary exponents as the sine function here. Then the next boundary condition. This is the right-hand wall of the box. In this case, what I'm doing is saying that the sine waves inside the box, they must have nodes. They must be 0 on the right-hand side of the box. That limits the values of beta, which was a smooth function. It can now only take particular values, these values here. And so I plug that in. And then finally, to ensure that the potential is 0 on the ground floor of the box, these coefficients have to be certain values, so that when you add up all these sine waves, you get 0 when you're on the ground floor of the box. Those coefficients have to be these values. They're only non-zero for odd ends, there's 0 for even ends, and they have to take on these values. And so this is the final solution to the problem. That's quite a bit of work to get to that one solution to the problem. You see the electrostatic potential falls off exponentially as you walk up the box. And you see in this summation here, this contains the x dependence of the electrostatic potential. And it ensures that the potential is constant, phi naught, over the ground floor of the box.